All right, hello lovely humans. In today's video, we are tackling differential equations. Woo! Don't panic, it's okay, it's okay. Differential equations just means anything with a derivative in it. So we have talked about derivatives a lot. And we have solved things like y equals, or wait, hold on, dy dx equals x, where we're like, oh cool, y equals the integral of x dx. Oh, look at that. Y equals 1/2 x squared plus c. Boom, that's a differential equation, and you can handle it. So I think one of the most important things in math is that we just are dealing with a lot of new language and a lot of symbols and terminology. So it can be intimidating, and that's why we are going to talk about it piece by piece. So I'm going to break this video into two parts, and then in next week's video we're going to dive deeper into some more complex examples of differential equations, because to do quantum mechanics, we really need to have a solid understanding of this suite of tools. It's okay if you aren't comfortable wielding them on your own. It takes a lot of practice, and I get it. I understand if you're not wanting to put in 10,000 hours of practicing differential equations, that's fine. But it's really important to at least be able to follow along, and to do that, I'm hoping that these couple of next videos will help you to be able to follow along in quantum mechanics, and or if you pick up a quantum mechanics textbook, you'll have a much better understanding of what's going on. Cool. Okay, so the first thing is that we are going to dive right into an example. So I'm going to steal this example from one of my favorite math textbooks, Mathematical Methods in the Physical Sciences by Mary L. Boas. She is a boss. So this example, I'm going to read it to you from the book, and I want you to follow along very carefully and write down, giving you a little assignment here, write down any words that jump out at you as maybe being important, and then I'll come back and we'll talk about that. Okay, example 1. The rate at which a radioactive substance decays is proportional to the remaining number of atoms. If there are n0 atoms at t equals 0, so if there are n0 atoms at t equals 0, find the number at time t. So I wrote this down really quick, and I'm actually going to move this. So at t equals 0, and then what is n at t equals t? Okay, cool. So some of the key words that hopefully you pulled out were rate. That's just a derivative, no big deal. So the rate of decay. So this is really important because decay means something is decreasing. So in this case, our rate, which is the change in the number of atoms in our sample over time, is going to be negative. The other key word, or I guess keywords, were proportional. Woohoo! So directly proportional, or just proportional, means that we have some constant. I'm going to label it lambda because because that's kind of the convention for this particular equation. But lambda is just some constant. And right now, we don't know what it is, because in this example problem, I didn't tell you what the substance was. Maybe it's carbon, maybe it's uranium, maybe it's lithium. This value will change depending on the type of substance that we're talking about. Okay, and then the last thing is that it's proportional to the number of atoms in your sample. Boom, that's just n. N stands for the number of atoms in your sample. So this is the differential equation that we are starting with. A couple of words on terminology. Words and terminology are like the same thing. Anyway, so this is a first order differential equation, which really just means we're dealing with one derivative of n or a first derivative of n as opposed to a second derivative. So if we had dn squared dt squared equaled some stuff, this would be a second order differential equation. d3n dt3 would be a third order differential equation, and so on. So this is a first order differential equation. And one of the other key things to note is that, well, one, it's ordinary, which is good. We're dealing with full derivatives here. And it is separable, which means that I can kind of pull the pieces apart and move the n's to one side and get all the t's on the other side. And that will help us to solve this equation. So let's do that now. Yay. Okay, so the first thing that we need to do is, like I mentioned, kind of separate the two sides and get all the n's on one side. So what I'm going to do is I'm going to divide by n and multiply by dt. Let's multiply by dt so we can cancel it first. That'll be a little bit easier. So dn equals negative lambda n times dt, and then I can divide by n, and that gives me just 1. Woo, there we go. Okay, so now I can actually integrate. Woohoo, party! So the integral of 1 over a constant is the natural log of that constant. And we're going to have, since these are indefinite integrals, we have to do our due diligence and add a little constant. So I'll just say that's c1. Lambda is just a constant. Oh, so we get negative lambda t plus c2. Boom. And so, since I want to be lazy, we just have constant c1 and c2 here. I'm going to be like, we're going to write c3 equals c2 minus c1, and then we're just going to get natural log of n equals negative lambda t plus c3. Okay, and now I can solve for n by using this feature, e to the natural log of x equals x. So if I take e of both sides, I will get out n, sneaky, sneaky. N equals e to the negative lambda t plus c3. And actually what I can do also is if I have e to the a plus b, that just equals e to the a times e to the b. And if you'll notice, since c3 is just a constant, I can write e to the c3 as just another constant, which I'm going to label capital A because I can. You can pick a different letter if you want. Okay, so now we have n equals a times e to the negative lambda t. Boom. All right. Now we get to plug in this initial condition. I'm calling it an initial condition because it is some values that we are given at time t equals 0, aka when we start our clock. We know that the sample size that we're starting with has a number of atoms denoted by n subscript 0. It's okay that we don't have an actual number for this. This is one of my favorite things. It's different between physicists and engineers. If this is an engineering textbook, they would tell you exactly what that number was, but since it's physics, they're like, it doesn't really matter. We just want to understand the math behind this. So anyway, so what we do is we plug in these values and we use that to solve for A. Okay, so at t equals 0, we plug in t equals 0 here, and then we substitute, we would substitute n subscript 0 into here. So we would get n0 equals a e to the 0, which just goes to 1. Oh, look at that. A equals n naught. N naught is another way of saying n subscript 0 that one of my physics professors would say all the time. So that is our equation. Yay! And since that's really all the information we were given, we're like, all right, dust the chalk off of my hands and we're good to go. Okay, so this procedure is actually really common in solving these types of first order separable differential equations. Unfortunately, not all differential equations are this straightforward, but a lot of them are. And I like this example because it's really useful. This is actually how we do carbon dating. So in this case, we would start with not necessarily an initial condition, but a final condition. So let's say we find a rock and we're like, how old is this rock? Or like we find a skeleton and we're like, how old is this skeleton? Well, we can measure the amount of carbon that is left in a particular sample. Maybe it's like from a bone or something like that. We can measure the number of atoms that are in that bone. And then we can use that to solve for the time that our sample is, or the time that has passed since our sample was created. And so this constant lambda here that's going to change depending on the type of substance that we're dealing with. Like I mentioned earlier, if it's uranium, it's going to be a lot bigger. If it's carbon, it's going to be a lot smaller. So another way to write this, just to kind of give you a sense of what this means, is that the original sample is going to decrease over time at a rate e to the lambda t. Cool. Okay, so let me just, oh yes, I was gonna say, let me check my notes so I figure out what I'm forgetting to mention. So I want to really emphasize that this is a fairly general solution. Oftentimes when we're doing applied mathematics, like in physics or engineering or chemistry or what have you, we're looking for a very specific, particular solution. The particular solution is going to change depending on your initial conditions, your boundary conditions, meaning like what constraints are on the system that you're looking at, and other information that you have available to you. So what this represents is what I would call a general solution that actually can be applied to many different situations. So this equation can be applied to many different elements on the periodic table, and also many different combinations of elements on the periodic table. So this is a general solution. What you would do to get a particular solution is you would say, okay, well, I have carbon. Let's use that to plug in the value for lambda and then solve for a particular solution. So this is pretty typical of differential equations. You're almost always going to get a general solution, and that's going to represent kind of what you might think of as like a family of solutions. So equations that all can satisfy this original differential equation. And if you're looking for a particular solution, that's when you need to solve for these constants that you get throughout that process. But sometimes it doesn't matter and you can leave with the general solution, and that's totally fine. It depends on what you're applying it to. Cool, so I hope that is helpful. Please let me know if you have any questions about the way to solve a first order separable differential equation, ordinary differential equation, no partials here. And in part 2, we are going to tackle a little bit of a harder problem. We will deal with a second order ordinary differential equation. So check that out. And then next week, we'll look at some harder examples. Yay! Cool. Okay, see you in part 2. Woo! Or not 4, but 2. Yes.